Hey, this is Mr. Ayton. This is Pre-AP Chemistry. We are Unit 5 Intermolecular Forces, and we are in Week 9. If you remember in Week 8, what did we learn about? We learned about physical changes, right? The breaking and forming of intermolecular forces of attractions. We took a look at the strongest intermolecular forces of attractions. We took a look at covalent network. We took a look at metallic. We took a look at ionic. And this week, we're going to be zeroing in on that covalent or molecular intermolecular forces of attractions. We're going to be taking a look at what's the difference between polar and nonpolar and the three main types of covalent or molecular intermolecular forces, which is hydrogen bonding, dipole-dipole, and London dispersion forces. So let's get to Week 9. What does polarity mean? What does polar mean? What does a dipole moment mean? It means when we have an electronegativity difference. If you remember, the most electronegative element on the periodic table is fluorine, which means fluorine, electronegative means attraction for an electron in a bond. If you have fluorine and fluorine, which one wants the electron more? Neither want the electron more. Neither attract the electron more. They have the exact same electronegativity, which means there is no electronegativity difference, which means this is nonpolar. It's a nonpolar bond. They share these electrons equally. But let's say we have something like hydrogen and fluorine. Fluorine is going to attract the negative electrons more because fluorine has the highest electronegativity difference, which means it will have a slightly negative dipole moment, which means the hydrogen will have a positive dipole moment, which makes this molecule what we call polar. This molecule now has a dipole moment. You can see water, oxygen has a higher electronegativity, so oxygen attracts the electrons more within this bond, which makes the oxygen have a negative overall dipole moment. The hydrogen side of the molecule will have positive dipole moment. And since this molecule is what we call asymmetric, it is not symmetric. If water was linear in shape, these dipole moments would cancel out. There would not be a positive north side and a negative south side. You can see there is a negative dipole moment on one side of the molecule and a positive on the other, which means this molecule is polar. So you need two things for a molecule to be polar. Number one, there must be an electronegativity difference. If there's not an electronegativity difference, it is nonpolar right away. But there also has to be an asymmetry in the molecule. If you remember carbon dioxide, oxygen has a higher electronegativity, which means oxygen is going to attract the electrons this way, oxygen is going to attract the electrons this way in a bond, and therefore you have a negative side and a negative side, and the positive is in the middle. You do not have a negative and a positive polar side. So carbon dioxide is nonpolar because of the symmetry of the molecule. So you need to have an electronegativity difference, and there must be an asymmetry in the molecule, which means polar molecules are going to have stronger attractions, because if you have a polar molecule, there's a positive side and a negative side. This can attract another polar molecule, which has a negative side and a positive side. The negative side of the fluorine is going to attract the positive side of the hydrogen, and this will create an intermolecular force of attraction. Not a bond, but an attraction. That's what intermolecular forces are. They are attractions. The strongest of those polar molecular attractions is called hydrogen bonding attractions. And you'll never hear me just say hydrogen bonds or hydrogen bonding. On a test, it might say hydrogen bond or hydrogen bonding, but I will always say hydrogen bonding attractions. Why will I say hydrogen bonding attractions? Because a hydrogen bond is not a bond. It is an attraction. It is an intermolecular force of attraction. And so this is an attractive intermolecular force between two highly polar molecules. You can see water right here is a great example of something that has hydrogen bonding attractions. The oxygen is very negative. The hydrogens are very positive. It's a very highly polar molecule. Therefore, you can see, since another molecule is going to be positive and negative, this forms an attraction which we call a hydrogen bonding attraction. This is a very strong, relatively strong. Not as strong as ionic, not as strong as covalent network, not as strong as metallic, but a relatively strong attraction. And so in order to boil water or to melt water if it's a solid, you have to break these attractions. Not the bonds, but attractions. Can you see why I don't like the term hydrogen bonds by itself? Because it is an attraction. You can see we can also have something like HF. HF is another great example of hydrogen bonding attractions. The F is very negative, and the hydrogen is very positive. And you can see there is an attraction here. And this is a hydrogen bonding attraction. Another great example is ammonia, NH3. Ammonia, we have N with 3 H's. The nitrogen is very negative. The hydrogen sides are going to be very, very positive. And so these are polar molecules. That's a negative, sorry. Positive, 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 which means this can form a hydrogen bonding attraction between these molecules. Okay? Do you see how these intermolecular forces are always between molecules? They're not inside the molecules. They're not intra. They're intermolecular forces. They are between two molecules. It is a force of attraction between two molecules. And so you can see hydrogen bonding is when we have F, O, or N, of very electronegative elements attracted to the hydrogen there, okay? Then we have dipole-dipole forces. Dipole-dipole forces are the same as hydrogen bonding attractions, but just weaker, okay? They're not as strong of a intermolecular attraction because they're between two polar molecules. You can see, remember, hydrogen bonding is between two highly polar molecules, whereas dipole-dipole forces are between two polar molecules, okay? So if you had, remember you have NH3, so let's say you have pH3. You can see phosphorus is not as electronegative as nitrogen, which means it's going to be a slightly negative, and so we have a slightly positive, and slightly positive. Just not as positive and negative as we had with the NH3. And you can see this forms an attraction. It's a weaker attraction. It's called a dipole-to-dipole force of attraction, a dipole-to-dipole force, which means it's going to take less energy, relatively, less energy to break this attraction than to break the hydrogen bonding attractions of NH3, because it's not as strong of an electronegativity difference, which means it's not as polar of molecules. Well, if we had HF, another great example would be HCl. Remember, chlorine is not as electronegative, which means it's not going to have as much of a negative side. The hydrogen is going to be not as much of a positive side, which means this attraction is going to be weaker than the hydrogen bonding attractions. We call that a dipole-to-dipole attraction. Okay? And so it's not going to take as much energy to break this dipole-dipole attraction as something like HF, which is much stronger. And of course, we have H2O, which means we would have something like H2S, would be very similar to H2O, except just not as strong. So you can see these are both polar forces of attractions, polar intermolecular forces. Hydrogen bonding attractions is much stronger than dipole-dipole attractions. So these are both polar. So you might ask, well, what about nonpolar things? Well, nonpolar things are, they exhibit an intermolecular force called London dispersion forces. And these are instantaneous attractive forces, whereas this one is kind of permanent. You can see there's a negative and a positive. There's a negative and a positive. This is like a permanent magnet. But this one is not permanent. This is just instantaneous because electrons are moving around. And so when electrons are moving around, if they're on one side at one point, just for a split second, you have a negative side, right? It's just instantaneous polarities. But this is for non-polar substances, okay? Things with carbons and hydrogens, like CH4, are going to have London dispersion forces. So if you see carbons and hydrogens, yeah, it's probably going to have London dispersion forces because carbon and hydrogen essentially have very, very relatively the same electronegativity. So it's kind of like a nonpolar molecule. Something like nitrogen gas, nonpolar. Which one wants the electron more? Nitrogen. It's a nonpolar. Something like hydrogen gas, something like oxygen gas, something like just an atom like neon, okay, these would be all nonpolar substances. As well as something like fluorine or chlorine. Here's chlorine gas. Chlorine is a gas at room temperature. This is bromine, which is a liquid at room temperature. And here's iodine, which is a solid at room temperature. You can see these all have London dispersion forces because they're all nonpolar. Now you might say, Mr. Ayton, why is chlorine a gas, whereas bromine, the weakest intermolecular force, is a liquid at room temperature? And why is iodine a solid? Yeah, it's got London dispersion forces. Why isn't this not a gas? Why is this a stronger intermolecular forces than even, say, something with hydrogen bonding like water? Well, something like iodine has so many electrons. These electrons are very polarizable. You have what's called polarizable electron clouds. And so when you have so many electrons, and these electrons can make this molecule instantaneously very polar, okay? It can be so polar, it has such strong attractions, you have a solid, even though they have the weak London dispersion forces. So the more electron clouds you have, the more chances you have of having instantaneous polarities, okay? So this was Unit 5, Intermolecular Forces, Week 9. Make sure you kind of understand when we hit after our covalent network, our metallic and our ionic, we have our molecular. And our molecular can be broken down into polar and nonpolar. It can be broken down into hydrogen bonding and dipole-dipole, polar, or nonpolar, which is London dispersion forces. And we'll get a lot of practice at this in class, taking a look at molecules, taking a look at these intermolecular forces of attraction. See you later.